Okay, let's take a look at these two application problems. These are both applications of the mean value theorem. And this is really the best way to think of the mean value theorem. Mean value theorem says if you know the average rate of change, you know you hit that average at least once, as long as you meet all the conditions. Okay, so number 190 here, you pass a police car at 10:17. Let's call this time 0. So let's say that's t equals 0. And let's say your position right there, let's say this police car is at position 0. Then, so however many minutes later that is, let's see, 53 minus 17, 36 minutes later. So at 36, you've gone 39 miles. So here's a second point. So that's your time, that's your location. So your average rate of change, your average speed is the distance you traveled, 39 miles in 36 minutes. Oh, well, I kind of want to be in miles per hour. Oh, maybe we should convert everything into miles and hours instead of minutes. Oh, so let's think about this. This was minutes. So 60 divided by 36 would be 1.67 approximately hours. So 0, 0, 1.67, 39. Now I'm in hour. I did that backwards. I realized as soon as I wrote it. 36 divided by 60. 0.6 hours. So there's hour and there's miles. Then my average rate of change would be my change in position, 39 minus 0, over my change in time, 0.6 minus 0. I did 39 miles in 0.6 hours. 39 divided by 0.6, 65 miles per hour was my average speed, my average rate of change. So all it is distance divided by time. That's all it is. Rate equals distance divided by time. So the mean value theorem says there must be at least one spot during that time when I was going 65 miles per hour. How do we know we can use the mean value theorem? First, the function has to be continuous. Position is always continuous. You're driving down the road, you can't teleport from one spot to another. Your position is continuous. Also has to be differentiable. We have a continuous function here. That doesn't necessarily mean differentiable, but velocity is always differentiable, or position is always differentiable, and our velocity will always be continuous. So remember that for your physics classes later. Your position function is always differentiable on any open interval. So we meet the conditions of the mean value theorem. I went 39 miles in 0.6 hours. That's an average speed of 65. There's no way that's possible unless I went over 60 at some point. In fact, the mean value theorem says there exists at least one spot, some C, in the interval from 0 to 0.6 hours, some time in that time frame, when my actual velocity, my instantaneous rate of change, was 65 miles per hour. So can the cops give me a speeding ticket? Absolutely they can. Like, this would hold up in court. In fact, they do this. Like this is a real world application of the mean value theorem. Okay, here's another example. It's basically the same example. So we got two cars. Car one takes off. I don't know how it's driving, but at some point it reaches this other stoplight, this other spot. So they're going from one stoplight to the next. So here's stoplight number one. Here's stoplight number two. In the same amount of time, car number two hits the stoplight at the exact same time. Both of these position functions must be continuous and differentiable. The mean value theorem applies. The question is there ever a time when they're going the same speed? Is there a moment when they're going exactly the same speed? Now, the mean value theorem just says for this top guy, there's some time when he goes his average. And the bottom guy, there's some time when he hits the average, but those don't have to be the same time. This guy might hit the average velocity at this moment, and this guy might not hit it over here. So we can't just directly apply mean value theorem. We got to think a little harder. We got to define this new function, h of x, or h of t, which is the top minus the bottom. Or let's call it first minus second. The difference between these two. So this h here is measuring this distance here. Well, I know h of 0 is 0. And I know h at time number 2, let's call this t2, is also 0. They start at the same spot, they end at the same spot. The difference in their positions is 0 at the initial time and the final time. So this is Rolle's theorem. Rolle's theorem says if this function is continuous, which it has to be, because both of these are continuous functions, the difference of continuous functions is continuous. And if this function is differentiable on the open interval, which it is, the difference of differentiable functions is differentiable. So Rolle's theorem applies. And Rolle's theorem says if your starting and ending values are 0, or even the same, they don't even have to be 0. So if I were to graph h versus t, my starting and ending values are 0, then there must exist some point in here, someplace in the middle, where the derivative is 0. If your starting and endings are the same, they don't have to be 0. These happen to be 0. The difference between their positions at the start and end are both 0. So there exists some c in that time interval from 0 to, what did I call it, t2, when h prime equals 0. So that means the speed of the first minus the speed of the second at that moment c is 0, or in other words, they have the same velocity at that time. Now, I keep using these words interchangeably. I want you to keep in mind speed and velocity mean different things. Velocity is a vector. It takes into account position. Speed is the absolute value of velocity. So if the velocities are the same, the speeds will also be the same. So is there ever a time when they're going the same speed? Yes, there is. And the proof is through Rolle's theorem, which is a corollary to the mean value theorem. And that's a good place to stop.